Ladies and gentlemen, we are on notes 1.4, which are on parent functions. Just a quick reminder, there was no paper for you to follow along with that I gave you in class for this video. So I need you to take notes on your own paper, please. And you're going to need graph paper because we're going to be doing a lot of graphing out of our parent functions, okay? So if you notice right here in this picture, it says beautiful dance moves. And these are actually some examples of some parent functions that you guys are going to be learning throughout this semester. So a parent function, what it is just simply, so I want you guys to write a definition of what a parent function is. It's just simply the simplest or base function in a family. Okay, and at this point in time, you guys are familiar with two of the different types of parent functions that you're going to be learning throughout this semester. The two parent functions that you are familiar with are the linear function as well as the quadratic function. So if you take a look at what we have right here with Desmos, so if you notice right here, we have f of x equals x. This is the most basic linear function you could have. It has a y-intercept of 0 and it has a slope of 1. Okay, but then we can start to get into some other types of functions. So I could say like g of x equals x minus 5, right? Or I could say h of x equals negative 1/2 x plus 7. So these are all examples of lines, but they're all based on the original parent function, which is y equals x. Okay, another example right here is I could have y equals x squared. That's our base quadratic function. That's the simplest quadratic function we could have. But we could start to change things around a little bit. So I could have something in standard form where it's 3x squared minus 8x minus 7. And here's another parabola that I have. Let's make this a little bit higher, plus 1, for example, right here. So here's another example of a parabola. It's not the parent parabola function, but it still is a quadratic function. So it's part of the quadratic family of functions, okay? Just like the other ones were part of the linear family of functions. Another example could be in vertex form. So I could have 3 times x minus 1 squared plus, let's say, minus 4. For example. So again, here's another parabola that's part of the family right here. And let's make this negative so you can see that it could also be an upside down parabola. And it doesn't matter whether it opens up or down, as long as it is a parabola, it's part of the quadratic family of functions, okay? Where the parent is x squared. All right, so let's get into it. We've got several different types of parent functions. The first one is the linear function. You guys already know the linear function, so we'll go through this pretty quickly. So the equation of a linear function, I'm going to say p of x is equal to x. Why am I using p? Because p stands for parent. That's just a personal preference. You can call it whatever you want. Most of the time you'll see it as f of x, okay? So now what I'm going to do is I want to graph my function. So I need to first of all set up my x and y axes. And I think going by ones right here would be an appropriate scale. So I'm going to have 5 and 10, and I'm going to have 5 and 10 here. And you probably don't have a graph set up, so you're probably going to need to pause the video first, get your graph set up, and then come back to me when you're ready to move on, okay? So we know that with a linear graph that it starts at 0, at this function right here, the y-intercept is 0, and that it has a slope of 1. So it's going to go up 1 over 1, up 1 over 1, or I could just make a chart for x and for p of x, for my inputs and my outputs. So when my input is, for example, negative 3, my output is the same thing as whatever x is, so it's going to be negative 3. So right here, I can go to negative 3, negative 3. When my input is negative 2, my output is just x, so it's going to be negative 2, so on and so forth. Inputs and outputs are just matches of each other because it's just p of x equals whatever the x value is, okay? So then I'm going to go ahead and graph out my line, and when I graph out this line right here, One thing I want you guys to be aware of is that you need to make sure that you put your arrows on your line, because otherwise it's not indicative of the full entire parent function right here. So here's what my line is going to look like right here, and I'm going to make sure that it's going to go through my entire graph paper right here. Okay, so I'm going to extend it so that way it goes through. Okay, and that's just the parent function right here. So what are some special features of the parent function of a linear function? Well, the first thing that I want you guys to notice is that it is a straight line. Okay, that's really important. The next thing I want you guys to notice that the slope is 1. So m equals 1. Okay, and we also know that it goes through the origin. So it passes through the origin. Okay, and that it divides the plane in half diagonally. Okay, and then the last thing that I want you guys to notice is that it's only in quadrants 1 and 3. Remember, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. It's only going to be present in the first and the third quadrants. Okay, so now the next thing I want to talk about is the domain. Well, what x values work? Anywhere from my graph spans anywhere on the left side all the way to my right side. So it goes on forever to the left, it goes on forever to the right, so I can say that my domain is x is an element of all the real numbers. Every single real value will be part of my graph, okay? And then the range, it goes on forever in both directions right here as well, so I can say that my range is y is an element of all real numbers as well right here. Okay, and that's the basic gist of what the parent linear function p of x equals x is all about. Okay, all right, so now we're going to talk about a quadratic function, and the equation of the parent quadratic function is just p of x is equal to x squared. Same thing, I'm just going to set up my axes right here. Sorry, not 9, that should be y. And I'm going to have a scale of 1 again. So bear with me while I do this, and hopefully you can do this as well. Again, pause if you need to get this ready to go so you can follow along with what I'm talking about right here. So for the graph itself, in order to be able to do the graph of the function, I'm actually going to pick out some values. So I'm just going to go from -3 all the way until +3. Okay? So for these values right here, essentially what this is saying is to find p of -3, I take -3 and I square it. Make sure you put any negative values that are being squared in brackets. It's critical that you do that, okay? So when I do that, I end up getting 9, okay? To find p of -2, when I square that, I end up getting +4, right? When I square -1, I get 1. When I square 0, I get 0. When I square 1, I get 1. When I square 2, I get 4, and when I square 3, I get 9. So when I graph it out, I'm going to go to -3, +9, and I'm going to put a dot there, okay? Then I'm going to go to -2, +4, I'm going to put a dot there. -1, 1 is right there. I'm going to just keep going with all of my coordinates right here. 3, 9 is my last one, and this right here, this graph is the parent parabola, our parent quadratic function, okay? So we're going to say p of x here is equal to x squared. And I apologize, I forgot to do this on the last one right here. I'm going to say p of x right here is equal to x, okay? So now that I've done that, the next thing I need to do is figure out what are some special features of this graph. Well, first of all, it's a parabola, okay? Second of all, it opens up. Okay. Third of all, it has a vertex at 0, 0. Okay. And that it has an axis of symmetry is just simply the y-axis. So your axis of symmetry, if you remember that from grade 10 math, is just simply your y-axis. Or we could say it's the equation of the line is x equals 0. okay? And it's only in quadrants 1 and 2. All right, so now the question is, what's the domain of my graph? Well, again, domain is all my x values, and my x values can be any value on the x number line. So any number on the x number line will have a corresponding y value, no matter what it is. So the domain of every single parabola is always going to be x as an element of the reals. Okay, so now to find the range, I'm going to go from my lowest value right here. So first of all, the range is going to be all real numbers, but it's from 0 all the way up to infinity. So y is going to be greater than or equal to 0. Now, how come it's greater? Because this is a minimum. If my parabola opened up, if my parabola opened down, then it would be less than or equal to. But the parent function, the parent quadratic function, will always open up because it's just positive x squared, okay? And that's the parent quadratic function. Now we're going to talk about the parent square root function, okay? So it's literally exactly what it says. The equation of the function is going to be p of x equals the square root of x. Okay, and in order to graph this out, let's get our graph set up. So I'm going to put x here, y here. This is 0. I'm going to go by ones again. So I'm going to put a 5 here, a 10 here. I'm going to put -5 here and -10 here. And actually for my y values, I think I'm going to go up by halves. So this is a half. This will be 1. This is 1.5, 2, 3, 4, 5. You're allowed to change your scale from your x to your y axis as long as it's consistent along this specific axis. And now when I go ahead and I do my graph right here, I'm going to have a chart, because this is going to really help me out. So now, if you remember in the last video, we talked about the fact that when you take the square root of any number, the number has to be not negative. So the smallest number I can take the square root of is 0. So when I find p of 0, I'm going to take the square root of 0, which is 0. So this will be here 0, okay? If I want to take this, if I want to plug 1 in, I'm going to take the square root of 1, which is 1, okay? If I want to plug in 2, I'm going to take the square root of 2, which is not a nice, pretty number. So I'm going to type it into my calculator, and I'm going to figure out what it is approximately. Okay, so when I take the square root of 2, I'm going to type 2 in, square root it, I get it approximately 1.414. So we're going to say it's approximately 1.414. So when x is 2, the corresponding y value is 1.414. So like taking the square root of 2 right here, it's not as useful right here to graph out 1.414. Obviously, you can use whatever values you want, and you can plug in whatever values you want, but I'm going to choose numbers that I can take the square root of evenly just so I can get my graph, okay? You might not always want to do that, but for the parent function at least, it'll be easier. So if I were to choose 4, I'm going to use 4 because the square root of 4 is nice and easy. The square root of 4 is just simply 2, okay? And then I'll also use 9. The square root of 9 is just 3. So let's go ahead and graph out this information. So I've got 0, 0. I've got 1. We'll go with 1 right here. So the next coordinate is 2, 1.4. So I'm going to put it like right here. Next I have 4 is going to correspond with 2. And then lastly, 9 is going to correspond with 3. And then I'm going to go ahead and connect the dots. And this right here is p of x is equal to the square root of x. So let's talk about some special features of the square root function. First thing is that it's going to start at the origin. That's important, okay? We also know that it's going to be in the first quadrant. So in quadrant 1, that's the only place where we're going to see the square root function, the parent square root function, okay? We also have that x and y have minimum values. So based on that, my domain is going to be restricted and my range is going to be restricted. It's not going to be just all real numbers. So for my domain, I'm going to say that x is a real number and that x is greater than or equal to 0. So, and how do I know? Because the x value starts at 0. And then for my range, I'm going to say that y is a real number and that y is also greater than or equal to 0. And I'm good to go for my information here because my values don't go below the x-axis, okay? All right, we have another parent function, and it's the reciprocal function. And if you remember, reciprocal just means that you're going to be flipping the value. So the reciprocal function is just plain and simply 1 over x. Now this one is a trickier function. So what I'm going to do right here is I'm going to label my axes, and this time I'm actually going to go by halves. Okay, so I'm going to label it as follows, and I'm going to go by halves. Okay, so now when I do my reciprocal function, I'm going to, let's start with -2. So when I plug in -2 right here, p of -2 is going to equal 1 over -2, or pretty much -1/2. Okay, if I were to do -1, p of -1 would be 1 over -1, or just -1. Okay, now p of 0 is where things get a little bit trickier. I'm going to do 1 over 0, and I'm going to try to divide 1 into 0 equal pieces, which is impossible. Remember, you guys learned in previous math classes that there's no way you can divide by 0. So 1 over 0 is just undefined, if you remember that. So right here, we're going to say that it's undefined when x is 0, okay? Now, if I want to do p of 1, I know that p of 1 is 1, because it's 1 over 1, which is just 1. And then p of 2 is going to be 1 over 2, or a half. Okay, so I'm going to graph these points out, and then I'm going to see what information I'm getting from my function here and see if this is really going to help me out at all. So at -2, I know that the value, the corresponding y value is -1/2. This is 0 here. It means it's going to be undefined. So at 0, there won't be a corresponding y value. There's no output when x is 0, when my input is 0. So I'm going to draw a vertical dotted line, and this line is called an asymptote. And what that means is that it's not going to work at this point right here. However, it's also an asymptote because of something else that we haven't really discussed quite yet, and we'll talk about that in a couple minutes after we finish graphing out the rest of these points. So at 1, 1, I have this point right here, and at 2, 1/2, I have this point right here. Now at this point in time, it's not really enough for me to really see what's happening. I can't really develop an idea of what's happening. So let's just try 3. When I plug 3 in, I'm going to do p of 3 is 1 over 3. So this value right here is 1/3. If I were to plug 10 in, it would be 1/10, right? If I were to plug in 100, it would be 1/100th. So these values are getting smaller and smaller and smaller. These values are decreasing. So what's happening is this is going smaller and smaller and smaller, but it's going to try to get really close to 0, because the larger the input is, the smaller the output is, because when you break one up into a lot of different sections, each section is going to get smaller and smaller and smaller until it approaches 0. So what this means is it's going to try to get really close to 0, but it won't touch 0, because when I take the reciprocal of a positive number, it still stays positive. Okay, now let's see what happens as I get closer and closer to the y-axis. So let's figure out what p of 1/2 is going to be. So what that means is it's 1 over 1/2. But when I have 1 over 1/2, it means 1 divided by 1/2, which is simply 1 times the reciprocal. Remember, when you divide, you just multiply by the reciprocal. So you end up getting 2. So again, since it's the reciprocal function, we can say, I'm just going to continue my chart over here. So x and p of x. We can say we can just take the reciprocal of our value. So when our value is 1/2, our output is going to be 2. Okay, when our value is 1/3, our output is going to be 3. When our value is 1/10, our output is going to be 10 because the reciprocal of 1/10 is 10. When our input is 1 over 100, our output is going to be 100. So as this value gets closer and closer to 0, the y value, the corresponding output, is getting larger and larger, and it's going to try to approach infinity. So that's why this is an asymptote, because it's going to get larger and larger and larger. It's going to try to touch the y-axis, but it can't, because I can't do 1 over 0. So that's what this side of my graph will look like, okay? And then the same thing is true for my negative values. So instead of using positive 3, let's use negative 3. That means the reciprocal would be negative 1/3. The reciprocal of 10 would be negative 1/10. The reciprocal of 100, negative 100, would be negative 1 over 100. So this value is trying to get closer and closer to 0 without going above 0. Okay, and then these values are all going to be the opposite sign as well. So it's going to try to get really close to the y-axis, but it just can't. And that's what my reciprocal function looks like. So some special features. First of all, if you notice, it'll only be in quadrant 1 and quadrant 3. Okay. Second of all, if you notice, you have a vertical asymptote at x equals 0. Okay, that means it's going to try to touch 0, but it just can't. It's going to approach it, but it just won't be able to. We also have a horizontal asymptote at y equals 0. So it's going to get really close to the x-axis, but it just can't touch it, okay? So now for our domain, every value that I plug in will work. So we're going to say our domain is going to be x is an element of the reals. Every value that I plug in will work except for 0. I can take the reciprocal of any number that's given to me except for 0. So this is going to say that x is an element of the reals except x can't equal 0. Now for the range is going to be any output that I get could be any real number, because I can, any input that I can have any type of reciprocal of it, except the only number I can't get from taking the reciprocal of another number is 0. Okay, there's no way that the reciprocal of some number will result in 0. So y will not equal 0. And you can tell from the graph as well, it tries to touch 0, but it just can't. Okay, all right, last function is the absolute value function. This one's not bad at all compared to the reciprocal function. If you remember absolute value, the notation for it is just simply bars around the x. Okay, so let's go ahead and do a chart so that we can have some values to plug in. So we'll go from -3 all the way up until we get to +3. So if I were to do the absolute value of -3, I end up getting just 3. So this right here is a 3. Okay, if I were to take the absolute value of -2, I get 2. Don't forget, the absolute value is the distance away from 0. On the number line. So -3 is 3 steps away from 0. -2 is 2 steps away from 0. -1 is 1 step away from 0. And I can just keep going with that. 0 is right on 0, so there's no distance for that. 1 is 1 step away from 0, 2 is 2 steps away from 0, and 3 is 3 steps away from 0. So I'm going to go ahead and set up my axes. So I'm going to label this my x-axis, my y-axis. I'm going to label this 0. I'm going to have a 5 here, a 10 here, a 10 here, a 5 here. I'm going up by ones. Okay, and if I were to go to -3, 3, this is where my graph would be. Go to -2, 2, this is where my graph would be. -1, 1. So on and so forth. Now, if you notice, it looks kind of like, when you finish it up, it's going to kind of look like a parabola, except it's really essentially just 2 lines put together. So let's go ahead and graph this out and see what this is going to look like. So here's my first part of my line right here, and it's just going to look like that. And then here's the other part of my line. So I'm just connecting my dots. And I know it's a line because it's going up and over or down and over by the same amount. That's how I know it's two separate lines, okay? Right, so for some special features, we know that the graph goes to the origin. And actually, this has a special name. If it was a parabola, we would call it the vertex or the minimum point. But here, this actually has a name called a cusp. And this cusp right here is where it's like the V part of your graph. And this is something you're going to learn a little bit more about when you're in calculus, but just so you know, it's called a cusp, okay? We also know that the graph is pretty much just two lines put together, right? The absolute value function is just one line going this way and another line going in the opposite direction, okay? We also know that it's going to be in quadrant 1 and quadrant 2, okay? And those are really the key pieces that we have right here, okay? Now, for the domain, any x value that I put in here will work. I can take the absolute value of any real number and I'll always get a corresponding y value. So my domain is going to just be x as an element of the real numbers, okay? But for the range is going to be everything above this line. So we know that y is an element of the real numbers, but remember when I take the absolute value of any number, the answer is either going to be positive or 0. So 0 is the lowest value it could possibly be. That's the smallest output I could get. So y has to be greater than or equal to 0. Okay? Make sure that if you have any questions, you let me know next time I see you in class, and I hope you have a wonderful day. See ya.